Good morning, everyone. Welcome to Prime Time at the Bethel Library. The Friends of the Bethel University Library collaborates with faculty development and other offices on campus to bring you programming that celebrates learning in and beyond the classroom of Bethel faculty, students, and staff. We're so glad you've joined us. Mark your calendar for October 14 at 11:15, when students from the Pietas Honors Program will be presenting their research and work. Today we welcome Dr. Julie Hogan, Assistant Professor of Physics and the 2021-22 winner of the Faculty Excellence Award for Scholarship. Faculty Excellence Awards are awarded every year in the areas of teaching, scholarship, and service. Faculty members nominate their colleagues for these awards, and the Professional Development Committee selects the winners. The awards are presented at faculty retreat by the person who nominated the winner. In Julie's case, she was nominated by Department Chair Brian Beacon, who, in short, in many words, he had much praise to say, described Julie as a home run hire for the Department of Physics and Engineering, and whose research record is second to none. Today, Julie will introduce the Compact Muon Solenoid experiment and share her group's physics goals, along with their contributions to the detector, education and outreach, and increasing diversity in CMS research. Let's welcome Julie.
Awesome, thank you. All right, let's get the share. I know how to do all of these things now. Awesome. Okay. Well, it's really a great opportunity. Thanks for letting me come and talk. It's fun to talk to audiences like this where everything is a little bit less technical, which you'll be glad to hear even before I get started. And I can just kind of share the broad overview. So there's not a specific, let's say, physics result I'm going to try to teach you about here. We're just going to lay out everything that's going on and what is my experiment and research program. So three kind of major outline points here. I'm going to introduce to you what is high energy physics, what is this CMS or Compact Muon Solenoid experiment, and what can Bethel do? How are we participating? How are we making a difference? So high energy particle physics, this is one of my favorite cool artistic pictures of our accelerator where we kind of have the accelerator like going out into the beyond or something. That's artistic, not what it really looks like here on the right-hand side. But high energy particle physics is essentially the study of fundamental particles, fundamental forces, where these are particles and forces that we don't interact with in our daily life because they require extremely high energy conditions to exist. And those high energy conditions don't exist naturally in the universe anymore. So to build this up, this has been 100 years basically of periodic discovery. And so we, particle physicists, have a model that we put into a table, kind of similar to the chemists, to categorize all our fundamental particles and forces, most of which are pretty new in terms of the history of science. So this time period around the turn of the 20th century was a big, exciting time period in physics because we were going from this scheme of, let's say, chemistry dominance almost, where you were discovering all the elements and categorizing all the elements into the periodic table. And at the turn of the 20th century, physicists discovered the subatomic particles that kind of gave a smaller picture. There were only let's say 3 particles needed to make all of those different elements that the chemists had discovered. But technology began improving, and we could do things like look at particles coming from outer space that were coming down onto the Earth. We call them cosmic rays. And some of the particles that were observed in these cosmic rays that could now be seen because we had the technology to see them, they didn't fit in any of those molds. And so all of a sudden there was an open door that there might be more things out there than just made up our picture of chemical elements. And that continued in the field that we call particle physics. So throughout that century, there was just an explosion of discovery of different particles. And so it almost seemed like we had gone from many elements to few back to many. And so the model that we call the standard model kind of collapses that back down to as few fundamental particles as possible. And so just like the chemists have their table where you go down and things get heavier, for those of you who haven't taken chemistry in a long time, as you go down, things get heavier, and as you go across, things have different properties, so the different colored columns, let's say. And our table, we kind of build it up the same way. If you come around the physics department, we have these magnets on our fridge. This is the set of magnets you can buy from CERN. So, we have no idea what they look like. It's probably even ill-defined whether they look like anything. So we just have these fanciful pictures. But we can sort them into property groups, and we can sort them into things that get heavier and rarer as you go down. So these guys up here are what we're familiar with building up all our chemical elements. And the big celebration that happened, let's see if we can get Zoom to go away, about 10 years ago, was that we had the last piece, the last hole in this picture was discovered at the Large Hadron Collider experiments. It's called the Higgs boson. So the Higgs boson, I like to share this little information because everyone has heard of this particle, especially, it's popular to talk about it on the science blogs and stuff like that. And why we need this particle is because we actually have no means of predicting what all the masses of everything else should be. They're measured properties in the model. They're not predicted. The model doesn't say, here should be this particle and its mass should be this number. We have to figure out what they are. And so Peter Higgs is one of the physicists who came up with the theory that would describe how this works. And so we can describe this Higgs field, which exists everywhere in the universe, as a group of physicists at a party. Whoops. Group of physicists at a party. I'm going to let the expert actually describe it for you.
Like this. Suppose there is a large cocktail party at the CERN laboratory filled with particle physics researchers. This crowd of physicists represents the Higgs field. If a tax collector entered the party, nobody would want to talk to them, and they could very easily cross the room to get to the bar. The tax collector wouldn't interact with the crowd in much the same way that some particles don't interact.
Oops, sorry. I'm just going to try and get rid of that.
Like this. CERN laboratory filled with particle physics researchers. This crowd of physicists represents the Higgs field. If a tax collector entered the party, nobody would want to talk to them, and they could very easily cross the room to get to the bar. The tax collector wouldn't interact with the crowd in much the same way that some particles don't interact with the Higgs field. The particles that don't interact, like photons for example, are called massless. Now suppose that Peter Higgs entered the same room, perhaps in search of a pint. In this case, the physicists will immediately crowd around Higgs to discuss with him their efforts to measure the properties of his namesake boson. Because he interacts strongly with the crowd, Higgs will move slowly across the room. Continue our analogy, Higgs has become a massive particle through his interactions with the field. So, if that's the Higgs field, how does the Higgs boson fit into all of this? Let's pretend our crowd of partygoers is uniformly spread across the room. Now suppose someone pops their head in the door to report a rumor of a discovery at some distant rival laboratory. People near the door will hear the rumor, but people far away won't, so they'll move closer to the door to ask. This will create a clump in the crowd. As people have heard the rumor, they will return to their original positions to discuss its implications, but people further away will then ask what's going on. The result will be a clump in the crowd that moves across the room. This clump is analogous to the Higgs boson. It is important to remember that it is not that massive particles interact more with the Higgs field. In our analogy of the party, all particles are equal until they enter the room. Both Peter Higgs and the tax collector have zero mass. It is the interaction with the crowd that causes them to gain mass. I'll say that again. Mass comes from interactions with the field. So let's recap. A particle gets more.
So that's the winning explanation, and we all rely on it. It's shockingly realistic of what this party would look like. In Dig Fifth, we had rival lab rumors coming in the door. But so this is what was the final piece. This particle, that Higgs boson particle, is the final piece of the standard model that was predicted but not discovered until 2012. July 4th, they had a big press conference to announce it. I was a baby grad student at a conference in Germany, and we all paused the conference to watch the live stream, expecting that it wouldn't be quite a discovery. It would just be a really nice announcement of a new result. And lo and behold, both the big experiments had discovery threshold statistical significance in their bumps here that are shown by the red line. And this had been a long period of waiting, because we can't just say, oh, there's one, I found it, it's this one. There's no way we can do that. We have to wait for the data, which is shown by the black dots. We have to wait for the data to be, significantly different from our predictions, which is shown in this case by all the blue and the green. So as we collect more and more data, the difference between the dots and the blue line becomes bigger and bigger, and so there's obviously something that's there that our model doesn't already include. And in this case, the red line was the prediction of what the data might look like if it was a Higgs boson, and you can tell that it agrees pretty nicely. The red line and those black dots are agreeing well. So that was hugely exciting, and here's the conference room at CERN. Here's Peter Higgs, accepting the accolades of everyone, everywhere. Now, that was 2012. The Large Hadron Collider experiments had shut down for a period of upgrades. We were going to significantly increase the energy of the collisions so that we could access higher mass particles. And the expectation was that we would have another discovery. It was really exciting. Everyone was just waiting for it to turn back on and give it a year to analyze the data, and we'll have all our new Nobel Prizes streaming in for all the new physics we've discovered. That was 2012, and now it's 2021. And we have not had any of those discoveries of anything. So this is confusing. It is not what anyone expected. And so we're stuck in a place where we're searching extremely broadly for new physics, because we have some problems that we know are out there and have no current solution according to the standard model. And we were really hoping that those solutions would have shown up in the intervening 10 years, and they haven't. One problem is that the Higgs boson mass we observe is quite light. I'll talk more about that later. One problem we have is that gravity is kind of hanging out separately from all the other fundamental forces with no mathematical description that can be integrated. We can't talk about them using the same mathematical language, and that seems confusing if we hope that they have, let's say, a similar origin in the universe. We observe that our universe is full of stuff, and we observe that whenever we try to make stuff, we also make anti-stuff, and these things can annihilate each other. So it's a little bit confusing that there's so much leftover stuff in the universe. We'd love to understand that. We observe problems in our galaxies. They're not spinning correctly. They're spinning as though there's a lot of matter out there that we can't observe through any of the normal force interactions that we're used to in the universe. That's confusing. And we would love to understand why we have 4 different forces. We would love to understand whether the origins of those is a single force or what. So all of these things we're looking for answers to try and understand these questions. And the list of questions, it's a little embarrassing, the list of questions hasn't changed in a long time, because we would hope to answer our questions and maybe then get new questions, but okay. We've been stuck on these questions for quite a while, but unfortunately, all we can do right now is look as broadly as we can. And so we do this using our tools, our accelerators and our detectors. So this is a picture of me and some students back in 2018 when we went to Fermilab to visit one of the detectors where I did my PhD research. But now I work on an experiment at the Large Hadron Collider. So it's a big accelerator underground. I got this awesome book when I went to CERN last time, The ABCs of Particle Physics. And as you can imagine, A is for accelerator, which makes things move fast. There we go. So that's what an accelerator does. It makes things move fast, very fast, very fast. And basically the idea is that we want to create conditions in these collisions that mimic what we believe to be the conditions at very early times in the universe. So we can try to learn from a lab condition what particles and forces existed at that time in the universe. And this is equivalent. Really high energies means really hot temperatures. And so this is well beyond the temperatures of like the insides of our sun, is what we're studying. The accelerator itself is basically a system of magnets. Okay, which is another letter in here. I think it's M. M is for magnets, directing particle beams. So that's what we use our magnets for. We direct the particles around in a circle. We need electric fields, which are applied with radio frequency cavities. That's this picture on the left. That speeds them up. And then the magnets, which are these supercooled, superconducting magnets, bend them around in a circle. And then we have the actual detectors. So we need two tools, accelerators and detectors. And D is for detector. And D for detector is my favorite, because this is actually the CMS detector here in this cartoon for letter D. And it's been operating for a long time now, and it was in development even longer than that. And it's built up of a lot of different segments, which you can easily see in this picture. And all those segments are optimized with different technologies to do different tasks. So we have some detectors in the center that are basically, it's basically a 100 megapixel camera, like you might have on a big telescope or something. 100 megapixel camera. The special thing is it can take a picture every 25 nanoseconds, which your phone will never be able to do, even if you spring for the 100 megapixel phone camera that will inevitably exist in a couple years. Outside of that, we have some detectors to measure energy, calorimeter, like the word calorie. I like going to CERN and get my Coke, and it doesn't tell me how many calories are in it. It says energy. It's like in joules on the nutrition label. So that's what we're measuring here. We're measuring the energy of particles. And we bend them in a magnet, in a solenoid magnet. So that's part of our name, Compact Muon Solenoid. And the big part, the big recognizable part on the outside are our muon detectors, which is basically just another way to track a certain particle that we expect to travel all the way through the detector, and we can identify it. The collaboration is very large. So we have about over 200 institutes from all over the world, and we're a group of about 2,000 PhD holders, about another 1,000 graduate students, and about another 1,000 undergraduate students, including some Bethel students. And what was really exciting earlier this past year, just last December, we had this new paper published in Physical Review D, where Bethel showed up on the list as institution number 149. And we had been, you would have seen this name on the list before, but only because of me. This was the first paper that also had this number 149 show up next to a student's name, which was really exciting. So we had a student also in this paper. So what can Bethel actually do? How do we participate in this experiment? This is just a smattering of pictures of my students and I over the last couple of years. We have a lot of projects going on and a lot of fun contributions. So perhaps the most central thing we do is we perform searches for new physics. So we are part of this huge team that's looking very broadly for all these different types of new physics. And we have one little piece of this pie, basically. So I'm going to go kind of quickly quickly through this, but basically the particles we're searching for are connected to that problem of the Higgs boson mass being too light. And so it was great to have discovered that particle, but it was confusing because while we were able to observe it in our machine, there's no good reason why we should have been able to, other than perhaps providence. So we can look at quantum mechanics to try to understand this. Anytime we measure the mass of a particle, what we're really measuring, what we really can see in our detector is what we'll call its normal mass plus all of the quantum mechanical junk that is going on, like in that flickering picture you saw in the previous slide. And all of the quantum junk has a mathematical formula. It should be basically the maximum energy that we expect the model to work at, which is large, times this relationship between the masses of all of a certain type of particles called bosons, minus the masses of a certain type of particles called fermions. And some of the physics students in the crowd will hopefully recognize those names by now, or will soon from your classes. And basically, this number is really large, and this number is amazingly tiny. And when we multiply something super huge by something amazingly tiny, we get something that's approximately 1, so that we can, we get a small number here that we are actually able to observe in our experiment. But we have no rational reason to explain why this number would be amazingly tiny. It's very unlikely that this is the full picture. It seems more like we could just shrug our shoulders and say, well, that's a nice coincidence. But that's displeasing. It seems unlikely. And so one of the ideas is that new particles could enter this equation that we don't know about yet. And so we need to keep looking for them. And we're looking for one of those types of particles. We call them vector-like quarks, which is a kooky name for mathematical reasons that I won't explain. But basically, they're quarks, but not really. They're quarks, but not really. They're kind of similar, but kind of different. This is the worst explanation in the world. They're kind of similar, but kind of different. The most important thing is that they're really heavy. A proton that you're familiar with is like 1 of these giga electron volts, so these are very heavy. And they do interesting things. They decay in interesting ways that look really cool in our detector and let us use a lot of fun algorithms to identify them. And that's what the students have been working on. So 6 students since about 2018 have been working on this. There's been 4 senior theses in our department and 2 talks at a national meeting. And basically, all of their work has brought us to a place where these numbers, which tell us the masses that we're sensitive to, and this is not public, so definitely don't look at this table. The masses that we're sensitive to are larger than they've ever been before, but in any of the searches done by any of the experiments. And that's really exciting. So we're on the road to publishing this paper, which is a little bit of a long road, but we're on the road. And so now we have to think about what we're going to do next. There's more data that will be coming in the next 3 years. And unfortunately, it's going to come at a much faster rate than it's come before. So there's going to be a lot of data to dig through. And basically, it's going to swamp our really, really rare, really, really heavy particles with what we call backgrounds. So we have to work on new strategies. We can't just keep turning the crank on what we've done before and expect to get similar results. So one of the efforts that we're going to do is look for particles that are produced more often. One of my students is already getting started working on this. Another thing we're going to do is use a new type of algorithm that's been developed. It's called recursive jigsaw, and it's really neat from a physics perspective because it takes our fundamental Lorentz transformations and it does them for like every single particle in the entire decay, which is cool. It's a really cool algorithm. And basically what it's going to do is it's going to give us a lot more handles. It's going to give us more variables. Everywhere you see a juncture here, everywhere you see a line, we're going to have angles, and we're going to have masses, and we're going to have information for every line on this diagram, which will give us more interesting handles on what's going on. But one thing I'm really excited about is this new model where we're going to take our particles, and instead of having them decay the way they did before, like this picture or like this picture, we're going to let our particles decay to yet even another new physics particle, the one called LQ. And this is a model made up by a Fermilab theorist who's basically been working on this model. And so I'm going to hook in with some of the scientists at University of Minnesota, and we're going to search for it. The next thing that Bethel students are working on is deep learning. So this obviously is a computer science type of topic. We use deep neural networks in all of our searches, mostly of two different types. Fully connected networks that have a whole bunch of, we call these little dots nodes, and you pass information from one layer to the next to create an output function. Another type is good for looking at pictures. We use this to identify some of our objects in the CMS detector. So my students who were doing an Edgren scholarship a while ago, they did a big study with some of these networks to figure out which of our various options, there are a lot of neural networks on the market, which one is best for our use case. And so they were calculating, they came up with a way to calculate these curves where we crank up the momentum, the energy of our object, and we look and see how well the algorithm does at identifying it. So higher numbers here on this graph are better. And we ended up liking the red curve best. I know it's not the highest on this plot, but it was the highest in general if we looked at all of our different particles. And we were making plots like this and trying to make this diagonal line as yellow as we could, which would be the equivalent of making these graphs have higher values here. And so they chose this red guy, which has a certain name called DeepAK8, to use to identify our jets. And then what they did was they started building their own neural network. So rather than shopping around different neural networks for identifying one object, we started building our own to try and say which events in our data sample look like they might be our particle of interest, and which events in our data sample look like they might not be our particle of interest. And the output of their neural network, after a couple of years of optimization through the different students, we had 3 or 4 students work really actively on this, we have a great result where all of the colors here, which are the wrong answer, they're kind of flattish. There's a little bit of a peak here, but in general they're kind of flattish. And the black lines, which is the right answer, have this really, really, really steep, sharp rise, and in fact it goes off the chart here. And so computers are really good at telling apart the shapes of things that are really sharply rising versus being flat. Okay, so computer programs are good at telling that difference, and so we can feed this into yet another algorithm to try and decide whether we observe any of these signal particles. We also have students working on deep learning just to improve our process of running what we call shifts. So we have to actually monitor the quality of our data, just like any engineering firm has to monitor the quality of their products going out the door. We have to monitor the quality of our product going out the door. And we do this, unfortunately, by eye, a little bit by eye. So 2 of the students actually ran some of these shifts, and they were looking at histograms to try and see whether they looked good or bad. And so they've been working to add some new histograms that are going to condense some of the data into color maps like this. So the idea is that with a plot like this is time, on the bottom. Obviously, this is just a little test. It's very, very little amounts of time. But over a long period of time, you could watch for those colors to change. If they started to drop from being yellow toward being blue, something would be going wrong with the data. So that our students implemented these color maps, which are really helpful. And now they're looking at neural networks that could try to take many histograms into the neural network and flag the anomalies. So this type of neural network is called an autoencoder. And so they're looking at autoencoders to try to do anomaly finding. And if we get reliable autoencoders trained through work like theirs, we might be able to let that make the first level of decision making for us, let's say, which would speed things up. Some of those same students have also been working on the detector hardware itself. So this is the second part of our contribution, which is not physics or software, but it's related to the actual detector. Our detector is unfortunately going to die because we've been doing the equivalent of setting off nuclear bombs in the middle of it for for years now. And so after you do that for a while, the material gets damaged and you have to replace it. So we're trying to replace it with better technologies that will be a little more robust against all of that radiation. And one of the things we're replacing is our silicon semiconductor tracker. So we've sent some students to Fermilab. Kyle was working in 2019 on programming this robot. This robot can hold things in its hand, and it can move around, and it can go up and down, and it can scan, and it's got a laser. It can hold glue, and it can do all sorts. And so Kyle wrote a LabVIEW interface that would generate some XML files so that we could, the operator could plug in all the information they got about the piece they were building and keep it nicely in our database. So that was really fun. We've been doing some work at Bethel. We built this test stand. So Jack is sitting here with the microscope, which is looking at a piece of silicon, and here's their machinery stack, which they had to build a circuit to go in front of. It's sitting right here. Mark's looking at the view from the microscope. And it was really awesome to have students who could work on this circuit because I cannot build circuits. This is not my skill set, but it was their skill set, so that's important. Okay. They also machined a new piece of aluminum with nice vacuum ports to hold that silicon really firmly, and they wrote LabVIEW controls. Here's Jack showing his LabVIEW program to the group so that they could take electrical measurements on these little silicon test structures. And this past summer, another student, a pair of students, Sid and Julian, actually we got permission to go to Fermilab so they could use the training they got from the Bethel station to actually go. They had real sensors that they were visually inspecting here on a computer, just doing some basic quality control, visual inspection. They were confirming the manufacturer's specifications, which was basically that all these dots should be close to each other. Not a lot of outliers. Basically, they needed to know that the edges were cut flat. The manufacturer has a specification for how well they could slice the flat edge of this sensor. And it looked like actually the manufacturer is doing even better than they advertised. And that's the machine they used to make this measurement. What's coming up is even more exciting. Also, a different detector is also getting upgraded, and Minnesota, down the road, is going to have 10,000 motherboards that are going on that new detector that need to be quality controlled. And before those 10,000 detectors can be quality controlled, the quality control tests have to be developed, and the LabVIEW has to be written, and the Raspberry Pis have to be programmed. And we have to figure out how we're going to move 10,000 pieces through a university lab in some sort of catalogable way. And so that's something we've hooked in with them in a new NSF award to work on. So we'll have students working a little closer to home, which is nice for many people. So in the last couple minutes here, I can share some of our education activities. So we have physics activities, we have detector activities, we have education and outreach activities, and this is kind of like a nice package of work in particle physics. So we've participated in educational activities at Fermilab. One of them is a hands-on tutorial where we try to basically take pixelated information from the detector and decode it. Your brains are really good at this. Pop quiz. Pixelated information. Abraham Lincoln. I accidentally asked that to a group of European students once and they didn't know who it was. Didn't work so well. But you all know who this is. Your brain has instantaneously decoded this pixelated information. Try these. Sometimes people can get the left plot.
Europe.
Sam, Europe, awesome. Anybody got any guess at the right one? A lighthouse, okay? Sunflowers. Melting watches, melting watches. It's really hard, right? I mean, there's no way you would get that. Your brain needs more data in order to give you that answer. You're never gonna get it from this much data. Okay, we have an algorithm we call particle flow that basically is a way of encoding all the rules we should use to do decision making, so we can start from the easy particles, then the medium difficulty particles, and then leave the really hard ones for last and categorize them. And we have taught students how to do this by putting together a Lego model of one of our collisions, and then the graduate students at Fermilab have to learn all the rules the computer is applying. And we've seen actually really good improvement in their ability to understand what's being done for them by the computer algorithms, their ability to explain to, let's say, a new incoming graduate student what their detector is doing. And that's very important, just as a skill. You know, if you're going to get a PhD in this, you should not just smile and nod at the computer and say, thanks, algorithm writers. You should attempt to understand what it's doing. So here are some cool pictures of our students putting together this model, and we're prepping a new one. We've done a lot of other education work. The modern physics students now do an exercise that uses some publicly available data from CMS, which we were able to present through the American Association of Physics Teachers in 2 different ways over the last couple years. And one of the students has really helped me with translating this into different computer languages so that we could share it with a broader audience. And this past summer, and actually the last fall, we've done also some outreach to the, let's say, the research community who is not part of our experiment, so theorists or others like that. We put on workshops so that they could understand how to use this publicly available data for their own research. And 2 of the students in particular this summer, they just did a huge amount of code development that we could be like the documentable example code for these professionals who are just not experts in our experiment. And so their work was of course cited in the workshop page and will live on in kind of our guidebook, which is really cool. The very last thing I'm going to share with you is some of the things we've been doing to improve diversity in our experiment, which is not super. It's not super. It follows the story of physics generally. Here's the youngest students, graduate students, PhD scientists, and then the engineers. And so the fraction of women just drops dramatically as you go upwards in age and as you get more technical in profession. And this is something that we would love to see improve over time, and these numbers become larger and people have more equitable access to our experiment. So I've been part of this committee since 2019, where we launched the committee to figure out what the collaboration wanted in terms of diversity and inclusion, which is how I made this word cloud. And one of the things they were really interested in was more mentorship. So I launched a mentorship program with a colleague from SUNY Buffalo, and we've repeated it for this year. So we're starting to pair up people in our collaboration so they can get career mentorship and other types of mentorship. And we actually also had a site visit. APS offers that they'll come to your institution and they'll survey how well how good is your work climate. And we actually had this done for our experiment this year, which was really informative. And so we're working on applying some of their recommendations. But this is something that's really a growing importance for our funding agencies. So we were actually asked to put together a plan for the United States group of CMS. We're actually asked to put together a document that outlined our diversity goals and our action items to get us there. And so this was actually reviewed as part of, this is basically how we work. We have a big NSF award to run the detector, a big NSF award to upgrade the detector, and everybody's got their little NSF award to fund their own students. So as part of the big NSF award to run the detector, we were asked to put together this plan to be reviewed by the panel at NSF. And so myself and a small group of other people in the experiment put together some drivers, what we wanted to do, and we built up a set of action items and a timeline for all of these things to take place. And lastly, as part of this big NSF award to upgrade the detector, we have a big plan for education and outreach. So we're going to use the fact that we have to upgrade the detector as a launch pad for some of these diversity initiatives. So myself and another liberal arts college professor from New York will actually be coordinating this next summer. We're going to try to get as many liberal arts college students, HBCU students, tribal college students as we can connected to these research institutions to actually help out doing some of this research work in the summer. So we're going to try to get summer students from outside the bucket of people who already have access to this type of research. Because most of this type of institutions don't have particle physics faculty who would be able to get their students involved. So we're going to try to reach out. We're going to try to improve the diversity of our student workforce and hopefully eventually of our graduate student workforce in this way. So that's really exciting and hopefully it will be successful. We'll see. So that's what's coming up. We've been supported by the NSF. We continue to be, praise the Lord, supported by the NSF for the next 3 years. And that's some of the work that I've outlined for you. So hopefully I'll have many more pictures. I don't have any good 2021 pictures except this one of Sid at Fermilab. Hopefully we'll have a lot more good pictures from summer 2022 and we can go out to exciting places and do fun things after our restrictions lift a little more. We'll pray for that. So thank you very much for your attention. It was nice to speak to you. Yeah, happy to answer any questions. A couple minutes. Yeah, Joyce.
I'd like to know how soon you're going to read your ABC book to your new members of the
ABC
family.
book. Well, I'm sure I'll read it in about 6 weeks. Maybe we'll have some engagement with the ABC book in a couple months. We'll see. Yeah, I got this about 2 years ago, completely way in advance. But now I get to read it.
So do you throw out the anomalies, or do you want to
Yeah,
look at them more closely?
well, obviously we will have shifters look at the anomalies, but most of them do get thrown out. We end up with a list of let's say, data samples that were high quality, and those are the ones we analyze.
Anomalies don't carry new physics?
Well, not anomalies that are coming from the detector itself. So these are things like this detector piece was not functioning correctly. So then we can't trust it, and we can't understand it. But we want that to be as few as possible. It's expensive to run. We don't want to throw out too much.
Is there a particular reason that the accelerator is all underground?
Yeah, there actually is, because we want to minimize the amount of disturbance, and we want to minimize the amount of stuff coming from outer space and mucking with the beam. So to combat both of those problems, you can bury it underground. good question. Okay, well, thanks a lot, everyone.